I think last time we started with 3, project number 3. So let's see. We're thinking about. I think let's go with Cheng Wang first. Cheng Wang, maybe we can update the recent result. Cheng Wang is online. Yeah, can you go with the
Yeah.
results? Let's look at the data and what
Mm-hmm.
plan going forward. I think we did the slow cooling rate for DJS and how's the paper coming along?
Yeah. I think, in the last 2 weeks,
Yeah, provide a quick
uh,
introduction before the thinking. This is what is the material and what is the thinking process.
in the material we use the previous, we published the 4% cadmium telluride doped and 10% selenide doped, co-doped silver antimatter telluride. And actually, we do two different experiments. The first one is that we did the post-annealing at the 200 Celsius for 24 hours. And the other one that Delvin and I were working together and to control the cooling rate from the melting status and to the room temperature. And so it's actually, if you can you see my screen right now? Can you see my screen? Okay. So this is a post-annealing sample. And at the first glance, actually, if you only look at the XRD powder here, if you only look at the XRD powder, actually it's very different from the slow cooling powder. Actually, the slow cooling is almost like the previous samples, and if you grind it, you you can imagine that actually you are grinding some crispy cookies, something like that. But the post annealing sample could be very resilient, has more resilience than
Mhm.
the slow cooling. Actually, it's very hard and not that shattered when you try to grind it into powder.
But how does it
So
compare to a standard, this, let's say standard sample, regular, without slow cooling? So you're comparing,
it's the same like it's almost the same like a slow cooling,
okay. So you
but
mean,
the microstructure would be the same as the post annealing sample.
the microstructure is the same for all of them?
No, actually no. But the post annealing sample is for the it you actually you quenched, right? Then you put it in the furnace for post annealing. But slow cooling is just you slow cool down to step by step cool down to the room temperature.
Yeah.
Actually, you can see the interface is almost like the interface here, interface layer here is almost like our previous work. So the microstructure won't change.
Sorry, which sample are you talking about on the left here? What sample are you pointing to?
This one is a post annealing
Okay.
sample.
And the bottom one is?
So right now you are looking at the post annealing sample.
Okay.
So you might see you can see the interface layer.
Mhm.
I always use the same scale bar. So
Mhm.
it's a 25, and our grain size is almost like 20 to 40, 20 to 50 microns.
Mhm.
And the interface in the embedded is very wide.
Mhm.
And for the post annealing samples, and I did a line scan on the. Actually, I zoomed in, right? It's almost like what we captured before,
Mhm.
but and then I draw a line scan in the SEM-EDX, and
Mhm.
you might see that
Mhm.
the selenium and the cadmium distribution, the orange and the purple line
Yeah.
is I think it's almost the uniform
I see.
than before, I
Okay.
think. And then you can also see the selenium here, right? You can also see the selenium here. Actually, it's
Yeah.
very homogeneous.
Yeah.
At least we can see from it. It's very
Okay.
homogeneous. Or we cannot tell it, in such scale.
Mhm.
But you'll see later that it's quite different with a slow cooling sample. And then actually, I detected the point analysis. Like here, this is the matrix. This is S1, and the S2 definitely in the interface layer, and the S3 also
Mhm.
in the matrix.
Mhm.
Then you might see that it's at least the silver atom and the telluride are almost the same. And I think there are some fluctuations on the cadmium and the selenium distribution, but I think it's much better than before.
So actually, the post annealing did, in terms of microstructure, it did exactly what we wanted it to do.
Yes,
That
yeah,
worked.
but I think it's just not very suitable for the discoded sample.
Yeah, maybe.
Yeah, and I put the electrical transport data later
Yeah.
in the next few slides. I'll show it later. I think if we facilitate the diffusion of the selenide and the cadmium, that may not be a good thing for our current samples,
Yeah.
but it's very promising for the
Yeah.
future if we choose some other dopant, right?
Yeah.
It's very promising. And this is the slow cooling sample. Actually, Delvin and I were working together. Actually, it's without Delvin's help, I cannot finish this experiment. And Delvin used PID control. And our recipe here is that we set the melting temperature at 800 Celsius,
Mhm.
and then we sustain the 700 Celsius for 60 seconds, and then 600 Celsius for 60 seconds, and then slowly cool down. Then we control the cooling rate to the 500 Celsius, and then natural cooling down to the room temperature.
Mhm.
And the only variables here is here, and others uh, were the same. So the only, I think, the manual intervention here is that we need to control the melting status. We control the 800 Celsius, and then we see the material melt.
Mhm.
So we skip this program, and then we make others the same,
Mhm.
like 600 Celsius for 60 seconds and 700 for 60 seconds. They are almost the same. It's controlled by the program itself.
Oh, sorry. What
Okay,
can we
so
do? Hey, can you hear me?
yep.
Okay. Why you stop at 500 C? 2 Kelvin, 2 degrees per minute can be
Mhm.
below 4 until 300 or 400.
I'm afraid of because it's in the open atmosphere.
I mean,
So
low cooling.
below the,
I mean, 500 C is still is kind of a high temperature phase for the sample. Like kind of
yes,
molten state, not melt, but molten state.
uh,
Uh,
yes,
I mean the diffusion. And okay, hey, later
around
we can
the
think about it. But
mhm,
so why you suddenly dropped 800 to 700 is faster, is it? After
800
melting,
to
yeah,
after melting.
800
Yes,
to 800
hmm
to 700 and 600, is it faster, the cooling rate?
no.
What is that? How much?
Uh, uh, I think probably later Delvin can show you the
Yeah, yeah, sure,
profile, the TT
sure,
profile,
sure.
and
I
you can
mean, the
see
main
it.
thing is
And
800 to 500, but you
mhm,
need to control that cooling rate if you want to
mhm.
be slow cooling rate. It's not like
No,
I
actually
don't know
the
about 800 to 700. How
yeah,
that is important.
the melting point of the theoretical metal is around 820 Kelvin.
Okay.
So probably it's around 550 Celsius. But
Mm. Yeah.
we don't know exactly because maybe the some dopant may change the melting point, right?
Yeah.
So that's why we start cooling at the 600 Celsius.
Mm.
And at the 600 Celsius, you can also see actually it's more like a mirror. It's like a liquid mirror
Yeah.
of
Okay.
the material itself. So it's still liquid.
Yeah.
But when
But
you cool
might be
down
out
the
surface.
500
Yeah.
Celsius,
Yeah.
yes, yes. And the why I stopped at 500 Celsius is because I'm afraid of being oxidizing of the sample because right now
Mm.
you
Yeah.
don't heat up the carbon, right? So it's quite in the open atmosphere.
Yeah, got it.
So
Okay, let's
it's
go.
easy to be
We'll see.
oxidized, I think. Yes.
Got it.
So this is the EDX mapping, and all the mappings are also in the same scale bar, right? As you can see that the interface, the green becomes bigger than before. And you might see there's a very thin lines here, but it's very easy to be indexed for there are some selenide. Sorry, selenium deficiency. It's, and this is another this is another mapping from the different positions, and you can see that the interface layer actually is shrinking. It's smaller and smaller. And then let's go to the 5 sources degree minute. And you can see in this mapping, actually, it's more evident that the interface layer is start disappearing, right? You can see here, it started disappearing. And the selenium is a little bit, it's also start to show the deficiency in this mapping. And it's the same for this one, but I think the green size, I don't know how bigger is it. Probably like this one, it should be, you see here is the 25 micron, but it's almost like, I think a few hundreds of micron, right? So I think this is what we expected before.
Yeah. Yeah.
And then this one, you see, this is a 10 celsius per minute. So for the 10 celsius per minute, it's a more faster cooling than before. So you see, actually, the interface layer is wider than the 5 Celsius per minute and the 2 Celsius per minute. And yeah, actually, the mapping is quite clear, and at least from the same recipe. And but for the XRD here, since we don't have I don't have, sorry, I don't have much XRD slot, so I have to give it a quick scan. As you see, this peak is not very obvious. So probably for this kind of sample, need to we still need to give it a slow scan for this kind of sample to show the small peaks. Let's see if it's silver two silver 2 tellurium, or the silver 5 tellurium 3 or something like that. And all the elemental distribution is here. You can see that only for the 5 systems per minute samples, there are a little bit, selenium efficiency here. But I think for others, I don't think, probably because of the SEM EDX has big error bar, but I don't think there are too many elements, too much elemental loss here. And then this is annealing data, post annealing. This is the electrical transport data of the post annealing sample. And actually the the transport performance changed after the 150 Celsius. You see, it's quite different trains as before. It's quite different, like it's also quite different, like the previous one we do the thermal cycle. I think it's just because the thermal cycle doesn't have enough time for it to go to have enough diffusion of the sample itself. And I think at the room temperature, the feedback drops because of I expected to have some silver telluride precipitate. So, but after that, I think probably we need to do some in situ XRD or high temperature XRD to see that what happened in this range. And this is for the different slow cooling rate samples, right? I would say that the transport data is quite difficult to analysis, because you see actually for the 2 Celsius per minute and the 10 Celsius per minute, the trains is almost the same, but I mean the CBAC trains is almost the same, but the electrical conductivity are different, right? Because for the 2 cells per minute, actually there are some semiconducting properties start showing up. I mean it starts showing up at the for the 5 cells per minute sample, then I think it's remains here. And so I think right now that's it for the last 2 weeks experiment. I might suggest that if we can change to some other dopant dopants, and then we'll also do the same thing for this kind of samples. I think it might, you know, I would say the interface layer can be suppressed completely, and if we give enough dopant and enough dopant inside the matrix,
Yeah.
then probably we can get this performance better and better.
So, I mean, firstly, like, really good job. Okay, you guys did amazing in 2 weeks with Delvin's help with the cooling rate, really fantastic. I think, as I mentioned, the microstructure is as expected. This is exactly what wanted to happen.
Yes.
And I think the purpose of this experiment, okay, for those who don't know, this was just like a Hail Mary, okay? Our Z was 2.3. We thought that if we can try these things very quickly, if the number goes up, then that'll support our paper quite a bit. Okay, so in the interest of that, I think the power factor values all at high temperature have dropped, right? I mean, our high ZT is high. So for all of them, the
Yep.
power is strong. So
Yep.
I think you should still measure the thermal conductivity. You have the samples left for thermal conductivity, right?
Actually, I think for the thermal conductivity, only the post-annealing sample and the 10 cells per minute sample can be measured, because for the 2 cells per minute and the 5 cells per minute, actually, it created more cracking inside the
Okay.
sample.
But
So
that's
it's
okay.
very hard to cut a LFA sample.
You can mention this in the, I mean, I'm just trying to think, maybe you can write this as either in your synthesis paper or some where you can say the whole point is we control the synthesis, right? So now what you've demonstrated is that you can actually get large grains, you have interface layers, you've stopped the diffusion of the interface layers, and you don't have transportation of all of them. I think this can go nicely into your synthesis paper because it shows the control that you're getting for non-interrupted synthesis. I think it's a really nice piece. It's not about the transport. It's mostly about the mic. So get better
Yeah.
quality feedbacks. I think you know, judiciously select which one you want to do stem on and check the element distribution, right? I think that's important. So that's, I think, good, really nice. The second thing, though, is that I think you might be right. The main problem in all of this is that there's not enough cadmium. So all of this cadmium, because it precipitated out, if you think about it, we stopped at 4%. Why? Because in your synthesis, in the original synthesis, we could see cadmium was precipitating out. Now we can solve that problem because you can get into the post annealing. So we should try to go back and before you even do any other dopants, you should try to replicate something we haven't been able to do with the DGS, which is higher cadmium. I think you should try 6%, 8% cadmium, because we know that what you put in nominally, you're getting much fewer. You put 4% nominally, you're getting 2%. If you put 6, you might get 3 or 4. So I think you should go all the way to 8 and 10. Remember the old, like, forget about selenium for now, right?
Yeah.
Yeah, I think that's what you perhaps should do next. But really, this needs to be done. Chengwang, you have to also, I will have a chat separately about your timeline and stuff, because really someone else should be helping you to do these experiments, right? So I think hopefully Yuting has, I don't know if Yuting has time or you have any of your people, they should be helping you to do this because you should be guiding them and they should be helping you to do these experiments.
Okay.
Right. So
Yeah.
please, so that you know the follow-up student is actually going to, I don't know if it's Jayant has time or not, one of the younger students needs to actually pick it up and do the experiments. I don't know how busy you think is the germanium telluride, And so, and also she's going to be transitioning and stuff. I don't know how much time they have.
Mhm.
Or maybe Delvin can do it if you. So this is for you to figure out, okay, with everybody. Christine, we have a lot of people. We have Jayanta, we have Yuting, we have Christine and Delvin. So with these folks, you kind of have to guide and say, let's go. And you do all the analysis, but they can help with the sample preparation, right? So
Mhm.
I would do 6%, 8%, 10% cadmium, and just do post-annealing,
Okay. Yeah.
right? So that we can try to. And the hypothesis you try and test that is simple. Do you see ordering or not? It is not so much about even thermoelectric. The whole point is to see ordering.
Okay. Yeah.
Now, the problem with all
Definitely.
of this is that the selenium co-doping has to be done initially. So now you have this issue where not only is the cadmium diffusing everywhere, so is the selenium. And that could cause a problem because your vacancies go. So it's going to be an issue, right? So when you do co-doped samples and post-annealing, you have to then, there's no way to introduce selenium later, you see. That's one of the problems over here.
Mhm.
I don't know how to circumvent that issue.
Can I interject?
Yeah. Go ahead. I think both you and Mahesh have something to say.
Why don't you try to dope cadmium with cadmium selenide instead of cadmium telluride?
Why? Can you explain?
Yes, different precursor, different melting point, different. It will affect the chemical. The more cadmium you add, the higher the chemical potential of cadmium goes. That's thermodynamics, right?
Mhm.
But maybe the problem is not adding selenium in a way that it doesn't get away, which means that you have to like change the chemical potential of selenium, which means that you have to add it in a different way. So adding it in cadmium selenide form, you might do that. And then you have a retention of both cadmium and selenium. And then what you have to tune is the tellurium.
I mean, the whole microstructures might be different compared to our old story. Like cadmium telluride, which we are using cadmium telluride, right? Then these are the microstructures being formed. If you cadmium selenide, might be different structures. Cadmium might be fully diffuse and uniform. Don't know whether you can get same structure or not. I mean, it's good to try and
I
see,
just
but
give an idea, man,
yeah,
like
definitely.
it or don't.
No, no,
But
no, no, no,
just an
no.
idea.
Maybe cadmium selenide much better than cadmium telluride doping. I don't know. Maybe you can get easily uniform without interface lasers. We don't know. Yeah, it's good idea to try. But these are the systematic. Right now, is everything going as a systematic? So you cannot compare exactly here. I
Chengwang, it's
mean,
your call. Okay. Chengwang, it's your decision now.
Mhm.
What do you think is the most logical step? To break down the suggestion a little bit. What that means is basically, uh, if you think about it, the obvious step is what I mentioned, which is just higher cadmium. Okay, that's obvious. And now you need to decide what happens. I don't have a picture in my mind. Maybe you guys can help me here. What is the selenium doing? Do you need to have a region where you have selenium vacancies? Is that good for your transport? How about microstructure? See, in your mind, you need this is, you're a fourth year now. Make your own decision, right? But it needs to be hypothesis driven. You need to make a table and say, what is the selenium doing to the microstructure and the transport? Okay, we know that selenium vacancies is good for p-type transport. Does it increase the doping? What happens to the microstructure when you have less and more selenium? Okay, I want to see that analysis. And then I want to see the thinking process. And then you make the decision. Okay, and then we discuss your decision and then we give you suggestions and you still do whatever the hell you want to do. Okay, that's what I want to see next. So basically, you form a table where you put in the selenium. And I would, this is what I would do. If I were you, I would sit down with a piece of paper, I'd put it down, say selenium. Okay, I know what it's doing. It's basically diffusing everywhere. This is causing p-type doping. I put cadmium. I want to get ordering. Ordering increases mobility. Now tellurium, there's going to be tellurium loss. If I do a cadmium selenide, am I compensating the tellurium straight away? Don't need more tellurium? There's all these things to think about. You need to navigate that space mentally, think about it, and come up with a decision. You don't need to do it now, but in 2 weeks, you need to come up with a decision of what you want to do next and what is a priority. Is that clear? So
Yeah.
I know Mahesh, hold on one second, let me just finish. Chema, for your synthesis paper, right? Please, I think you should think about wrapping it up, okay? Because I think we submitted this paper, you can't wait for too long. I think this actually connects nicely to what you already have. Okay, I think when the synthesis paper we did pure AgSBTE2, right? So there's not even cadmium. Forget about selenium, isn't it? So maybe what you should do is to do what I suggested now, which is do the exact same experiments, but just with some series of cadmium doping. Okay, it might take you another 1 month or something, but that data you see is the whole, right? If you think about the logic of the paper, because you have pure AST, you say you have synthesis control stopping the reaction multiple times. Okay, then what you should logically have done next, which we did not do because we were focused on the paper, was the cadmium series where you did, let's say, different cooling rates and post annealing. Right? So then what you would do last is the selenium core samples with post annealing and different cooling rates. So the only thing you're missing in the middle is the cadmium series. Right? And now, so you can test both hypotheses. What is the cadmium doing? More or less diffusion of the cadmium. What is the selenium doing? And then you say that with synthesis control, you're able to achieve all of these. And I think this chemical potential argument is a nice one because I think this is how, even in defect design and stuff, people use this chemical potential to guide synthesis routes and dopability, etc. Anyway, so we can actually use that information for the paper. Okay. So, but this is what I would require to is please write this down in the WhatsApp group chat. Okay, this is where we start off next week. Okay.
Okay. Yep.
Like, hypothesize. It's not just a data presentation. You need to present your hypothesis. What is the thinking process and the decision you made? If you started some experiments, great, even better, right? Along that line, that's completely okay because now you're mature enough to make your own decision. Okay. Sorry for Mahesh. Go ahead.
Yeah, sorry, it's very good. One is aligned with you. Don't change the dopants. This is the even though you got to know the interfaces are disappearing with the slow cooling rates, right? Selenium is diffusing anywhere everywhere is not true. Like is uniformly distributed across the matrix. Is selenium is pure, you are finding at the interfaces, right? There is selenium deficiency at the interfaces means most of the interfaces only because of the silver telluride or silver cadmium or cadmium telluride uh, in particles. So at the interfaces, selenium is always poor. The matrix is uniformly distributing, means selenium doping is good. It's not about diffusion everywhere. Another one is if you see the average GT may be improved. Like with the cooling rate, slow cooling rate, interfaces are decreasing. Nothing but cadmium is diffusing inside the matrix. It indicates, and cadmium diffuse inside the matrix indicates the semiconductor nature might increase more. So the Seebeck increase and the the electric conductivity decrease. It's good sign of cadmium diffusing inside the matrix. And the power factor is, of course, it decreased, but you need to improve the that I mentioned, you need to improve the cadmium more. Then see, it may improve the power factor. Right now, the average GT also will improve because cadmium inside the system, thermal conductivity may decrease more, and power factor is average GT can be improved because low temperature, the power factor is high. So the average GT compared to be high. These are the ideas, and stick to the same dopants and rich cadmium. Don't no need to go with new dopants, like as Kada said. Yeah, these are
Yeah,
the kind of points.
let's just get the lower hanging fruit done. Like you need to do more cadmium, more on the synthesis, more understanding of the microstructure and the dopant distribution. And then based on that, we can probably think about going after a proper campaign with a new dopant for AGSBT2. We'll think about it. I think the reason I'm emphasizing you should come up with your own hypothesis. Originally I remember you had a slide a year and a half ago, choice of dopants, the ionic radii. Okay, but there are clearly three effects. One is dopant diffusion, okay, one is ordering, and one is
Yeah,
interface layers that is unique to DJS. So you need to have a picture in mind of what each of these is doing with respect to the synthesis conditions. then we can predict what we want to do with the new dopants. Okay. So I'm not giving answers. I'm asking more questions intentionally. Please, it's for you to think and decide. Okay.
I mean, the cooling rate, the transport is not really uh, follow the trend, but you can try one more time if you have time.
What is
See
not
the
following
trends.
the trend?
There's 2 centimeter, 2 degree centimeter per minute, 5 degree.
In
The
terms of
transport, like
I don't
the
believe transport is precipitation. This is all error bar.
yeah, yeah. So it's not really have trend. So
If you
if you
talk about low temperature transport, I would believe trends. I
mhm,
don't say anything about the trends.
at high temperature, okay. So
So
then low
I would
temperature itself
I would do low temperature if you have I don't think you have samples right for low temperature.
it's,
Do you have
is
samples
okay.
for MS Chengwang?
Or you mean the sample for PPMS?
Yeah, do you have a sample of PPMS from these synthesis? No, right?
Yes.
Oh, you do? Okay. So I would
All of them, and post annealing sample and different slow cooling samples. I have a lot of it. It's just it's not. I'm not sure if it's proper for the LFA, but for the PPMS, not a problem.
I mean, I think you should do it. I think also Jayanta is learning PPMS. So it might be useful,
Yeah, Chingyun itself we can load.
can
Pawan will be around. Yeah, I mean, you
you
can load. You can
basically
make a full contacts and load.
the low temperature resistivity curve is an indirect indication of ordering. So you could maybe say at 2% cadmium, we already have ordering or less ordered domains. That's also interesting. So all of these things. So point is you have to use all this data to answer three questions, right? Microstructure, which interface layers, transport ordering, and I forgot. What's the third one? Atom diffusion or dopability. Okay. This is how you then
Yep.
formulate. Okay. Okay. Any other thoughts on this? If not, just trying to move things along because otherwise we'll be discussing it forever. Anything? Okay, so Chema, that's your to-do item next week. And let's catch up separately because we can plan out next 6 months and stuff, thesis and stuff.
Okay. Yeah.
Okay, let's move to what's next on where's my WhatsApp? Hold on. I think let's go to the top. This needs to be better organized. Anybody want to volunteer on taking charge of organizing stuff? You should. I don't know if you guys have seen the Notion page that Nongwei has created. I don't know. Maybe Andre knows how it is done, right? But Andre, you're not core part of this group. So, but basically, it's very nicely structured. Maybe Chengwang asked Nongwei, and I can ask you to also organize these tasks like Nongwei did. It's very, very nice because you can track all the lists and it funnels in very nicely to the papers as well. Okay. Anyway, I'll chat to this separately. Okay, let's go to copper titanium telluride. Jayanta. And also you have new samples from Partha, right? So maybe we can discuss that too. Yeah, we can see. Can you explain a bit more slowly? What is okay. Okay. Mm-hmm. Mm. Okay, so let me try to understand this. So as you decrease your SPS temperature, the lower SPS temperature gives you more copper telluride precipitates. Is that correct? Okay, that's expected. Okay, it's still there. Hmm, I see. The peak, very sharp at 600. Mhm. Mm.
Do you have XRD on before SPS, the powder on before SPS? Can you can you compare with force field? Which one? Okay. Uh-huh. I mean, the powder before SPS, you have so many impurity phases, right? Then repeat again. I didn't in SPS. Oh, okay, the jolly the initial powder. Mhm. I mean, you are able to get the phase, good phase, only at high temperature SPS. You don't want to go beyond 550 degrees centigrade because decomposition. You are unable to make a good phase with the low temperature SPS. So density is not good at low temperature. I mean, yeah, you can try some even whether it's decomposed or not. Whether this phase go with high temperature and fast cooling. I mean, don't hold the at SPS. Maybe instead of 10 minutes of dwell time, reach 500. Don't 10 minutes of dwell time, only 5 minutes. We generally go SPS current is lower slowly, right? Don't do that. You can switch off and come to fast cooling because height, yeah, according to 250, 350, and 450, the impurity phase is decreasing, but you are worrying to go at high temperature decomposition. So you can go high temperature 500, but don't wait. Don't be longer time. We do 10 minutes, right? Do it to only 5 minutes and then fast cooling as faster. Yeah. I mean, that's my suggestion.
Jayanta, the one idea to go to high temperatures, but okay, the main problem is that you don't expect your phase to be stable at 450, but it is in the SPS, correct? And secondly, it's fully dense. Like the density is really good. What other data did you looked at the sample, the SPS, you did transport, but did you do any other characterization? Like is the DSC, TGA, is that done on the SPS samples or no? Let's go to that data. Okay, this is what you were showing. So with an impurity phase, which is your data, everything is your data here. Okay, and let's look through this a little carefully. Wait. So cycle one, what is cycle two is slowing cooling down, is it? 450. 613 is 300 Celsius. So 300 Celsius, you have some huge phase change. Is that right? And at 300 Celsius, what you typically expect is your copper telluride decomposing into some copper telluride plus excess tellurium. Is that right? This is what people have reported, is it? And that's the bottom right curve, right? So what you're basically saying is that this 612 should be the same as this, and that's coming from these set of reactions. Is that what you're saying? But is this data on the bottom right? This is not your data, right? Data, okay, in this paper, is it done on copper telluride or is it done on copper tin telluride? This is just copper telluride. Okay. That's why their drops are also intense because it's the primary phase. Okay. Yeah, this you need to figure out. I also don't understand why this is happening. Very surprising. Where did you send it? Where is this in it? Oh, okay. They have. Okay, so you'll find out. I mean, the other way to do this is you pre-mix the powders, okay, and this is what Haiwan has been doing. Okay, you can take the same powder and he has temperature control for his synthesis with the carbothermal shock. We've done in non-contact. So we're not looking at densification, we're just looking at phase formation. And it sort of should complement your NCD-XRD, right? Haiwan, you know how to do this, you know. So you just take the powder and then you create a batch of 6, okay? And then Hyman knows how to control different temperatures. You can just anneal the different temperatures, look at the phase. It's very easy to do, right?
Yeah, something you can finish in 2 hours of time.
Why don't you do that with Hyman? This will complement your in situ XRD results. It'll also give us some extra information on whether this sort of technique that Hyman uses is complementary to in situ XRD. Okay. Of course, it's different because that one's a SPS, so that gives you. Anyway, let's try it. I would suggest to try this. Hyman can help you do the experiments. You can do the analysis and look at the phase evolution, and then let's compare the study. And
This
then
is
do this.
this is titanium based sample, so is very easily prone to get oxidized. So need to be careful.
You can do it in the glove box, not a problem.
Yeah.
I mean, we're looking at phase ratios, right? It's okay if it's oxygen, but yeah, maybe changes. I don't know. Okay, so let's go back. So that's interesting. Uh, coming, so coming back to your main question, why is it still stable at 450? So why do you think it's going to be unstable at 500? Maybe you should try the 500.
No. I sorry. That Kelvin, I thought like 550 degrees centigrade. Now when you go back, it was like Kelvin, the DSC. So it's already decomposition range.
Yeah, so that's what
Yeah. No, I mistake. I was like 550 degrees centigrade. No, it's 550 Kelvin. Sorry. Yeah. Then it's already decomposed.
that's right. But the point is that if it's stable at 450,
Then go with 450. Then decrease the dual time.
no, just go to 500.
More decomposed.
Well, apparently not.
I don't know.
613 is 300 degrees Celsius. You decompose completely, but some magic is happening. Your phase is still at 450. I would go to
Maybe
500.
under pressure. That
That's
is no
fine.
pressure.
That's
This is
fine.
pressure.
Yeah, that's
Mm.
what Jayanta said in the beginning. Now, the point I'm saying, how do you know that 500 degrees Celsius and the SPS pressures may not give you even better sample?
Don't know. Yeah.
In the point where it decomposes, right? Why don't you try that? You haven't reached that point yet. So I think you should do that experiment anyway. I mean, the goal is clear, right? So you do in-situ XRD, you work with Ivan, get the powder samples done, and look through the step-by-step phase composition analysis, and then try to 500 degrees Celsius. Because I mean, let's look at the thermoelectric data, right? Okay, let's go to the data now. Thermoelectric data. Hmm. Need to understand. Yeah, I mean, hmm,
What kind of phase transition?
we don't. The point is that it's supposed to be copper telluride, but it's a very minority phase in the sample, like 14% or something, 12%. So it should not give you such a big change in either the transport data or the DSC. So that's the mystery, right? Mm.
Can you reduce the step size here? You're doing the measurement,
But I think the trend will be the same.
or is this a trend or just like something
Right?
happening?
Yeah. Mm. The good news is your lattice, your conductivity is already pretty low, you know.
Thermal conductivity is low actually already.
So if you, for a new compound, if you're able to dedope, I mean, this is what the original idea.
Yes. Yeah, DDoP, yeah.
Let's get there later. I don't think you need to rush. Let's figure out what's happening in the phase transitions. You're still metallic. You have a lot of room. If you dedope somehow, you're able to dedope very nicely. Then you definitely your power factor will go up by a factor easily in order of magnitude. Then you'll be in some useful range, right? Like for on a ZT of one with no additional module is a very very good paper. Okay, so it's quite promising. Things, it cannot be something wrong. Correct.
Yeah, this looks okay. Looks okay. Yeah, because carry current is too high. You need to DDoP crazy. Can you actually, now you already know the carry concentration, can you get the effective mass using the Morse equation of this sample? Yeah, then you know that can.
So I think the rule of thumb, Jayanta, is every order of magnitude drop in the carrier concentration will generally speaking increase the mobility of one order of magnitude. So you look at the number now, 1.7, if you drop your somehow doping level to 10 to the power 19, you will end up getting a mobility of 170. You know, which is a
Yeah,
really
close
good,
to me.
that's fantastic. Okay.
Okay, maybe can you get the effective mass and maybe try to do some like modeling, then you have some idea what range of mobility expecting. Just plot some Pisrenko plot and all those things.
Yeah, so, I mean, I think it's still a little early. Uh, it's a good idea if you want to start learning about it. I think it's a good idea.
Yes, at least
Someone
learning
has
then
all
we
the
have.
code on this. So you can also talk to
Sure.
work with them on this. No problem. We have all the code for this. No, is it N-type?
Is metallic, so it's noisy.
That's okay. That's expected, actually.
Yeah.
I'll get better. So it's very good. I think it's really, I think it's very promising, man. I think you're getting, yeah, this is going to be fantastic. In small part, understand the phase transitions. Our synthesis is providing relatively high phase purity. I think it's looking promising. But the one missing from all this, Jayanta, is the things like EBSD. The thing we learned from our silver antimony telluride is we started doing all this too late in the process, and then we were then stuck. So I think it'll be good to understand what is, like, mobility is that number, but is the grain size still pretty high after SPS? So try to prepare some samples to look at the grain, just the microstructure. Ideally TM, I don't know how brittle this is. Like with SPS, is it easy to prepare do you need to do the pips, or is it possible to just do a regular FIP to prepare the cross section? These questions. Hmm. Is it easy? Easier than telluride? Okay. Excellent, excellent. Good. Hmm. Interesting. For thermoelectrics, we don't care. Okay, so I think it's an interesting question. Like, can you get a phase pure comp? And even if you look at silver antimony telluride, we don't get pure phase. Even if you look at his slow cooling that Cheng Wang has, it still has silver telluride peaks, right? Cheng Wang? If you look at your 2 degrees Celsius per minute cooling, do you still have silver telluride peaks in the XRD?
Yeah, I think so.
It's very difficult. I mean, you would have to change the stoichiometry quite a bit to get there. Okay, so what we learned is that for silver antimony telluride, even though it's a line compound, the eutectic happens slightly away from stoichiometry. So you should look at the phase diagram if something exists to see is it possible or not. Maybe it's simply a question that no matter what you do at the composition, you might not get the eutectic. You will not get the pure compound.
Selenium doping also at tellurine may help for both band gap opening, like decrease the Curie concentration and phase.
Year 3 for Jayanta. Not yet, right?
I mean, okay.
I think looking at the fundamental phase diagram is more important right now, more than any doping. Right? I know people always want to go start doping because we
No,
think
he did selenium 0.5. How is it? Very bad. I mean, yeah. Hmm. Yeah,
I'm
yeah.
personally very worried about doping. Before you know what material you made, you start doping it. You have no idea what you're putting in there, man. Like,
Silver is good.
something good is like you talk to any person doing thermoelectrics, they'll want you to dope anyway. Ask you to dope shit also. Doesn't mean you should dope it. So let's figure out what's happening first. It's the first time someone's made 90% phase pure compound, right? Don't forget that. Let's understand what's in there. What are the phase transitions? We can get to thermoelectrics. It'll be fast. Don't worry. Okay. Mhm. This is following up on Pepe's work. Copper germanium kernel. Okay. Mm-hmm. Sorry, I have to point this out because we have to point this out. But the exact other structure that we've been working on, that Pepe is working on, is a copper antimony telluride, which is 527. Right? With the
Same space group, by the way.
same space group, right?
Same space group. This is not new, man. Like frankly speaking. But anyway, go on.
Hasn't been reported before. Okay.
That's up to the community to figure out, man.
I mean, this material has been reported before or not? Hmm. 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 Awesome. You got full pure face? Oh my. That's crazy.
Yeah, he told.
How did you decide 600, man, not the higher temperature? Okay. Is this the current control that Delvin's built, or is it? Oh my God, this is insane. But you need a proper XRD, man. This is arrival refined. Is this good enough? I don't know. I mean, should we send it to a beamline, man? Like ask Partha is in France right now. I'm not kidding. I'm on email with him because I want to hire Amit. So I messaged him. I got the reference letter. We're good to go. So I'm going to start the paperwork. Send him a freaking sample, dude. Grind the shit and send it. Like, Partha, can you measure this point? I'm not kidding. Because if you want to show this, then nobody's made this variant. You might as well get the beamline data for this. Okay. Very exciting. Yeah. And this is fun. This is fun. Why Chris predict 5 to 7 for Germany? We would have solved the problem and we're done with it by now. Think about it, right? We had this 314 prediction for copper tin selenide. I wish we had the 5 to 7 prediction for germanium. By now we would have actually finished the validation paper. Crazy. Okay. Yeah. Hey, by the way, can you go back to slide 7? So here, this is for the selenide sample, right? Sorry, this is copper.
Same.
Telluride. Okay. So it must be some copper telluride phase that people haven't seen before that's giving you this peaks at 620 something. Right. Yeah, yeah. Have to. Yeah, I agree. Let's go back to the transport data. So your question is that if I do SPS 300 kind of measure transport, I mean, you still have the same problem. It's just that, in my guess at least, you'll still have the same problem, but the precipitation may or may not be good for you. I think do the experiment, right?
Yeah, the density is low right now, so you wanted to improve the density. It's good try.
I think it's a good idea because your density goes up. Your overall, even if you have some minority phase. Okay, okay. The key question would be if this large peak at 620 Kelvin is clearly not a minority phase, then it changes your transport completely. Like what happened in your samples. You'll see a big peak, huge jump like you saw in the other sample too, which may not be a good thing.
Yeah, that is kind of structural transition.
Yeah.
First order.
So before you do that, I think you should find out what's happening. What's this due to? There's not a decomposition, it's a phase transition.
Yeah, high temperature XRD definitely you will get to know, right? Most sudden jumps are first orders are associated with the structure, not decomposition. But is it slow? Yeah, decomposition. If not reversible, not repeatable, means decomposition. But you can see cycle 1, cycle 2 is repeatable, means not decomposition. I mean, I don't know. Yeah, can say.
Oh, it's crazy because like you have a compound, but the whole thing is undergoing a phase transition. That's right. This is a great beamline problem, man. Maybe we should get you some beamline. I will talk to Dongshan.
Just a comment. If samples looks like magnetic,
How do you know?
the trend of seebeck and conductor is like a parabola trend, right? Generally, it should be like a magnetic sample.
I mean, you haven't done PPMS on this. I guess you could do.
Yeah, because if it's metallic sample, the seebeck and conductor should go linear trend because samples are highly metallic. But it's showing parabolic trend, so means it has some magnetic property. Might have.
You can look into it, Jayanta, maybe.
Parabola should be linear.
Do magnetic there.
They have.
We don't have, but yeah, can. Someone
Low temperature
can.
Yeah, low temperature or high temperature VSM, right?
Yeah, high temperature one can.
Interesting. But not everything is about ZT. I mean, the fact that you're able to synthesize pure phase with DJS, I mean, what the hell?
And KL is good, right? You can dedope.
Yeah. First order. Let's solve the main problem first. Main problem that you need to solve is what is the phase transition, if at all? And then, yeah, understand the structure. That'll tell you the temperature range in which you can play with. And then dedope. Silver vacancy, I don't know, we'll think about it, right? Okay, but the follow-up to this is we need to get beam time, man. So talk to Partha, see what he thinks. We have a faculty here, Dong Shuang, who has good beam time in Japan, and she goes every 2 to 3 months. And for her, powder is free. She can just pop the powder and get you data. It doesn't even take, it's very easy for her to do. So you can even send her like 10 samples, she'll get you all the data in like 2 to 3 months. Okay, she can also help to do in situ XRD if needed, in situ beamline, like temperature dependent phase transition. So you check with Partha and his team, whoever synthesized it. If they want to do it, that's because I think Partha also has people he knows in France and stuff. Then it's okay. We can just wait for it. Okay, but the way this is going to work is you have phase pure samples already. Definitely, maybe talk to, do you know Feng Xia? Can you try to do a careful XRD and assign everything properly? Like long exposure time. Will this help, Pepe? Or is the data good enough as it is?
Can I see the XRD, please?
Slide 6. This is rapid, fast XRD. Oh, but yeah.
So the problem is that the peaks are very much moved. They are really far from the original positions, which makes me believe that you have germanium telluride. I could be wrong, and hopefully I am, because this data is awesome, dude. In fact, forget about the COP13 bullshit, like we send these samples here to LBNL and Peter will analyze it for us, right?
No micro ED on this, it's just XRD.
No, for sure. But like my issue is that the peaks are very much moved. Too much. A lot. That's a problem. Peak positions are, at least the number of peaks is the same. That's pretty good. Do you have any germanium telluride here? Do you have any ideas to prove that statement? Like, because the peaks kind of like, especially the main peak is where germanium telluride sits. And that is the first thing that somebody would say. So hopefully not. Like, let's eliminate every single possibility. Yeah, for sure. No. This is for you to like start like figuring out backwards, right? Like, because that's the first thing. Like, why are your peaks so far? Clearly, because your lattice has been distorted. By what?
It's not far means it's not either decrease or increase. It's just only the space increase, right? Between the different refinement. One peak is down, one peak is up. Means it's kind of a HKL. I mean, it's kind of a spaces between them with the conventional CF file is larger. The spacing is like, it's not strained, right?
I don't know. You tell me.
I mean, I could. I mean, from the you could see there is moved based on the peaks associated with the 12 refinement, right?
It's moved towards higher to theta.
No, one side if you see is down at below around 27, one side is up. It indicates it's not moved. It's move. It's like different edge scales.
Which edge scales?
I mean, the main peaks. I don't know this one. Like, which how do you say what? How do you say the mood?
Yeah.
Because forget about the after ball milling, right? Let's go to the Joule heated compounds.
Okay.
Right? They all move towards this side. That is a higher to theta. What that means is that the lattice is shrinking.
Yeah.
Because
okay.
theta and D spacing are inversely correlated. Okay? Which means that there is a compound or something, like for some reason your lattice is shrinking. That could be because of a nano inclusion or a doping. Germanium telluride is smaller than this, possibly. That could be the reason. That's why I thought, do you have germanium telluride?
Is there a systematic error of some sort that's possible?
Did you, Jayant, you did the XRD yourself, right? The only systematic error that could be here is sample displacements. Sample displacements is this. So this is your stage. Unless your samples is perfectly parallel to your stage, then there is a sample displacement. That is of the order of a few microns. This sample displacement is too large. And normally sample displacement is eliminated by using the same person experiments because we all prepare samples in the same way. My sample displacement for the AG2TE stuff is constant. Like, in fact, I can see which samples have Chengguang prepared because the last sample displacement is different. So between people to people is very, very constant. So if Jayant has done these experiments,
systematic error, it's too large to be systematic error, I think. Unless
Janta, can I?
different examples completely differently, it's odd. So I would say, like, let's do some, Janta, do some EDS. See if you have germanium telluride. If you don't, then that's a different possibility. We can look into it differently, right? So let's go to the most likely probability, which is that you have some germanium telluride that has precipitated. Hopefully not. But that 2 theta, that 27, that's where germanium telluride appears. So, I mean, hopefully you don't. And your real refinement is pretty good, man. Like, your values are fine. Your peaks are well fitted. Seems fine to me. Yeah. I mean, then if you don't, you don't. But we need to explain why your peaks are so far from their standard.
So my question is, where did you do the radical refinement? Is it in the same powder XRE data? So I think we also have nice 2 theta and stuff that you can do in IMRI, okay, which has a crystallography expert leading that effort. So because you're stabilizing this phase, I think it might be worthwhile to ask her which samples you want to, just to show her that you're getting this beautiful data. Like, can she help you do a better at her XRD? So if her stuff matches your results, then you're in good shape. This is what I would recommend. Okay. Let me connect you guys, and then you can just contact her. Okay.
You have copper telluride there. I can see it. You have copper telluride. Yeah, there. Yeah, there is copper telluride, which is fine. Like, an impurity phase is fine. It's completely fine, man. You're okay. But then that could be the reason why your peaks move. Like, again, like, you've made a phase and it's clearly the majority because your readable refinement is extremely good. There too. But especially in the first DDS map. I think
Janta, so Tianyuan and I, we have a lot of experience looking at nanoparticles. You need to use 7800 to see the precipitation phase in homogeneity. So 76 is just too old for EDX.
But Janta, even if you have the precipitates, doesn't matter. It's okay. You know, like, and actually they would explain why your peaks move so much. Honestly, like, either way, you're fine. So it could even be that by pelletizing, you precipitate something, right? You could have a pure phase from the very beginning, but then you know, like, it could be possible. And even if you had the precipitates in the powder, you'd be fine. Your level refinement is very good. Like, honestly, all the peaks are fitted, the intensities are fine. In fact, the fact that you have, like, a peak with the intensity not refined could be because it's a telling sign that you have precipitates. Because that intensity that you're missing is somewhere else. Right? That's what intensity in XRD means. But either way, you're fine. That doesn't matter, frankly speaking.
Okay, I mean, anyway, let's do better EDS. I think the point was whether you have phase pure or not. Let's also discuss that. I mean, maybe it's also all linked to your peaks at 612. So let's do that work carefully first. Okay, before you start to optimize thermoelectrics. I think it's really good work. I think it's getting there. And look at the phase diagram, man. I don't know if there's any information in the phase diagram here. You must. Yeah, check. Maybe you already checked it, but you can share it with us also. Okay, let's move on. Ivan, do you want to share about anything that you've been doing? You're next on the list. And then
maybe so this week
maybe Tianyan, he can share the carbon thermal shock things because he was doing like the automation and he can give everybody like a wrap up on how this carbon thermal shock was felt in the Science Advance paper and how we use alternative method to go through it.
Oh, so I just start share my screen.
So Tianyan, you're done. You're going back next week, is it?
Yeah, this week.
All right, this week. It's been a year.
So Tianyan, yes.
Good.
Hi, can you see my screen?
Yeah.
Okay, hi everyone. I'm Tian Yuan in our group, and I will introduce you my 1-year report of this project. First is some background on CO2 electrocatalysis. The selectivity of different metal catalysts in CO2 reduction reaction is significantly affected by their electronic structure and their intermediate binding strength. And it has been shown that the Cooper metal catalyst is the only single atom catalyst in CO2 reduction reactions that effectively catalyze the production of CO2 products. So we start our research in Cooper catalysts as this background. And I will introduce our previous method at first. Basically, we are just doing our experiment, follow the reference paper, which published in Science Advance. And the mechanisms basically are using cellulose as a carrier of Cooper chloride. And after carbon thermal shock, the cellulose will carbonize and the Cooper chloride will reduced into Cooper nanoparticles, which is benefit for CO2 products generation in CO2 reduction reaction application. And in the reference paper said that when the CTS temperature reached at 830 degree, at this condition, the Cooper nanoparticles distributions looks very uniform and the coverage is very high. You can see this you can see this picture. It is very hard to find a lot of empty space. So the distribution is very uniform and the coverage is very high. So it seems like very promising of these samples to for us to use in CO2 reduction reaction application catalysis. And based on this background, we start our experiment, follow the method in this reference paper mentioned. And we use ball milled cellulose and we applied stir and ultrasonic to make our cellulose solution. And we changed a lot of different parameters. And we use filtration as cellulose decomposition at first, as the reference paper mentioned. And we found the problems very soon that we can see the right SEM picture. The Cooper nanoparticles distribution is not very well. Like the number of the Cooper nanoparticles is very small. And the sample of the cellulose is bad too. And we suggest that it's mainly because the bottom is vacuum and there is a force that make the some cellulose drop down and the cellulose will lose and the coverage and the uniform turns very bad. So cellulose is a big problem that it is very hard to make a thin and uniform and high coverage cellulose layer at this original cellulose decomposition method. And after this, we optimize the cellulose decomposition method. We use a drying in the tube. Instead, we just the filtration, like the reference paper mentioned, and we found that the cellulose were not well distributed on the carbon paper better than our original method. And we can see the right SEM picture too. The carbon nanoparticles distribute more uniform, and the numbers increased a lot at this decomposition method. But we still found two issues in this Science Advance paper. The first one is the hydrophobicity. We found that after we do a carbon thermal shock, the cellulose will like shrink, and it will lead to a lot of empty space, which allow the waters go through, and hydrogen will generate, which is bad to CO2 products generations in CO2 reduction reaction catalysis. And the second issue is that the Cooper contact, it will lead the CV peak very low. As you can see, this is our CV test. No matter how many times of the Cooper on cellulose compare with the standard sample, the CV peak always very low. So, and you can also see this video. It illustrates that our samples in flow cell got very quick floating, which is bad to catalysis application. And based on this background, we start to think the cellulose layer distribution is a very big problem. So we have to change our previous method. Here is the mechanism of our original CTS method. It basically we using carbon paper as a substrate, and after we applied relatively high CTS temperature, it's like above 800 degree, and the cellulose will carbonized and provide high density of the defect sites, which allowed copper chloride reduced into copper nanoparticles. It seems like very promising, but it is very hard to repeat this sample because we tried a lot of times to tune in different parameters or different conditions of the experiment. So we start to think if we can just remove the cellulose layer, because the cellulose is a big problem in our previous test. And we developed our new thermal shock method. We start to use new carbon paper with one side already separating one layer of PTFE, which ensure the hydrophobicity. And we tested the substrate. It can normally work at the temperature not above 600 degree. So we have to find a new copper salt with low decomposition temperature, because the copper chloride got relatively higher temperature than this limitation. So we start to deal with copper nitrate, which the decomposition temperature is around 200 degree. And you can see the CV test looks very promising and good compared with the standard sample. The peak is higher, and it illustrates that the catalysis activity is higher. And also you can see this video. We also tested the hydrophobicity of the samples after we CTS at temperature 600 degree. It still remains hydrophobicity, as you can see. And after this, we start to add some very small volume of silver nitrate salt in our copper nitrate salt, because appropriate silver may lead the production of carbon monoxide, which can further reduce to CO2 products and improve the catalysis efficiency. And we do XRD, and we confirm that there are copper and copper oxide in this sample, but the silver compound is very hard to identify because the volume is too small. And we also do SEM and EDX here. You can see these two picture. Even in the background, the Cooper and the silver ratio looks good. It's like it remains in 9:1 as we added before, same as we added before. So it shows that the Cooper and the silvers mixed very well in this sample. And we also found that some parts of the silver and the Cooper were more likely to combine as a heterostructure, as the pictures show here. And after this, we start to think our previous samples is very hard to repeat because previous we just use our hand to do the drop cast, and the performance will different every time because after all we are just using our hand, so it's very hard to control the same condition. So we start to think if we can just build a automated sample preparation system by OpenTrons here. So we started in 3D print custom sample rack. We 3D print this custom sample rack for producing batches. As you can see, we can produce 6 samples in one time. Like it improve our synthesis efficiency a lot. And then I will introduce our automated dropcast controlling system. First is mix process. We will use the tip to absorb 18 microliter of nickel or silver salt at first, and then absorb like 162 microliters of the copper salt and mix them in a new tube. The process will repeat 30 times to satisfy the need that we want to synthesize 6 samples in one times. And after it mixed well, we start our dropcast processing. You can see the droplet is distributed very uniform as it. In here, the samples, the solution droplets are distributed very uniform, and it will not change as long as your coordinate is same and right. So it improved the repeatable of our samples. And we do optimize a lot of times for dropcast labware. At first, we just add 12 drop points each samples because we think it is enough for the solutions distribute uniform on our sample. And we tested the CV image, and you can see the peak is not high enough that we want. And then we added 10 drop point each samples. The CV peaks turns a very, very big difference than our original one. Like the peak is higher, obviously. And then we start to compare our OpenTrons sample with the best manual samples without OpenTrons. Because in this batches of manual samples is the best performance that we have ever synthesized. And you can see our new OpenTrons samples even got slightly higher peak than our best manual dropcast samples. So we believe that OpenTrons samples is promising because it still has some space to optimizing later by add more drop points. And it improved the repeatable of our samples. And after this, here is our conclusion. first we confirmed that the science advanced paper is very hard to repeat because the cellulose is a very big problem. It's very hard to make a thin and uniform and high coverage layer of cellulose. And in this background, we developed our alternative low temperature thermal shock pyrolysis by just remove the cellulose layer and find a new low decomposition temperature Cooper salt as an alternative. And the result proved that the electrochemically accessible metal Cooper is comparable to the standard samples as the CV showed before. And our open trans process is applicable to different precursors. For example, different Cooper salt, nickel salt, or silver salt, which could lead different metal oxide heterostructures and alloy formations. And that's all my presentation.
Nice. Let's go with questions first. You guys don't have any questions? I'm kind of familiar with most of this, but not the recent one, not slide 20. Nicely done. But...
I mean, I'm also not familiar, but hey, could you explain? Go to slide 20.
Slide 20 here.
Yeah. How this current is useful? Is the magnitude of current or peak is important? Both.
The top line is our manual samples peak.
Yeah.
And we test a lot of times, like our original manual dropcast samples. As I said before, it is very hard to repeat, and this is the best performance that we have ever tested. And our open trans samples is even better than our original manual sample. So I think.
How about the quantity of the sample? Did you normalize with the quantity of the sample? Like how many drops? Like quantity.
Quantity is same. Like we all use like 22 drop point. But original one, because we use our hand to drop test, and the location may not very uniform, I think. But the volume is same.
Okay, yeah, normalized. I don't have much question here. I don't know. Yeah.
I mean, the peak location tells you most likely what is the active metal, because you're doing it with a certain potential. And the peak height tells you that you have high electrochemical activity. To get to things like selectivity. You cannot have electrochemical activity just producing hydrogen, which would be really crappy. That's why I think we're waiting for the GC to come. When the GC comes, we'll do the experiments. How many samples do you have? 30, 40, 100?
I think now, because in the previous 2 weeks, Tianyuan has finalized the open trans for more repeatable samples. So in this week, he will try to prepare like one batch of like samples, each of them for a few in nitrate salt. And then we will pass it to GC and hopefully NMR a bit later when the lab is set up in Create. If this is good, that's pretty good. Tianyuan also has made like a few other precursors of samples, including acetate or whatever. So I really hope that within the summer we can finalize at least one of these papers within this technique.
Tianyuan, my question for you is, why are you leaving, man? Why do you want to do flexible electronics? It's a waste of time. I'm joking. What are you going to do? What are you going to do? Have you thought about what you're going to do?
Because I need to work at first.
It's okay. I'm joking. So what is your next step? What are you going to do when you go back?
I mean, I might work for Micron this August start in Singapore. And then I plan to like find if I can find I will try if I can find other like PhD opportunities in the next year. because this year the policy is a little bit influenced.
Okay. So, I mean, we will have a group. You've already done all this really nice work. Okay. So if you want to think about doing a PhD with us, let us know. Okay.
Okay. Thank you.
I think Ivan has recommended you before, and you already have the sample preparation. The next step is to actually start to do the electrochemical testing.
Yeah.
The work that you do in Ivan, if everything goes through, I don't know, okay, fingers crossed, but we recruited a student from Iran. She's like an electrochemist for your electrocatalytic project. I've already given the offer, but because she's Iranian, I don't know if her visa will come through or not. But
okay,
she will take your learnings and start to actually do the full electrochemical testing. And that's the idea, right? So I think to help Ivan. So, once you're sort of sure about it, you want to have a chat. The last thing I remember from you is that you want to do flexible electronics or something. So I was like, okay, I'm not sure what's the alignment there, but we can have a discussion.
Okay.
I'm going to be in Create tomorrow till Friday. Today, sorry, I had a department meeting. It's actually going on right now. I went for the first hour. I said, bye-bye, I need to go discuss science. So that's why I have to be in NTU. But tomorrow I'll be on, actually this afternoon, if you want to chat, we can have a discussion, Ivan, after the group meeting. Okay. But really nice work. Like, congratulations. I think I have seen versions of this. Ivan has presented over many, many months. I know the problem with the cellulose, and your 25 slides do not capture the effort that you put in. I know the effort that went into this, the cellulose and the hydrophobicity. Really fantastic. And you have to acknowledge, you have to have an acknowledgement slide. So you need to acknowledge Nippon, because it's Nippon's idea to try the different salt. Okay, so I think that was a clever thing which gave us the result, like at low temperature, that we can do it. So now, fingers crossed, we get some interesting results when we do the full GC test for CO2 reduction. Okay. But yeah, really fantastic. Please send me the slides, yeah? I would like to keep the slides. It's really nice.
Oh, okay. Thank you.
Any other thoughts? Ivan, do you want to say something as a mentor?
I would say Tianyuan has been like taking the initiative all the time. So he has been working very hard with us and with Chen Guan all together and with the group. So so I think Tianyuan is expecting to do a PhD. I'm not sure whether in our group, but at least somewhere. So let's keep in contact at least. And Tianyuan has also been helping like machine learning on the metastability part. Okay. So previously the model, actually some of the models was trained by Tianyuan because he was quite interested in training the models. So our ballpark discussion in the back is that Shiyun will take part of the synthesis from Tianyuan, and Tianyuan, once he's back to China, he will like help training the metastability model a bit, because I'm expecting of including an additional 50 to 60 new descriptors in the model training, and I think I will have a big problem on my computer.
Okay. Yeah, so they're going to stay in touch, and then for example, with Yuting, because she did her master's in MSc, of course, she has thesis. So we're going to put in her application for her PhD in Jan. And since you're already familiar with so many people in our team and what we're working on, please consider, okay, and we can chat about it in the afternoon, see what you feel like, okay? Okay, I'm just going to move on because of in time, okay? I have a hard stop at 12. I have to go back to the department meeting and show face, okay? Before they shut down everything. So I think, Pepe, you had something that you want to show with the germanium telluride as well, right? Andre was here. I don't know if Andre is still here.
There is quite a lot. I must save my catalysis slides for Wednesday.
Yeah, I think let's leave the catalysis.
I think I'm gonna leave Andre and Jayanta to do the talking for me. Like honestly, they're gonna be more coherent.
Okay, let's go.
Okay, let me share my slides.
This is a good problem to have, okay? When people meet every 2 weeks and there's too many results to share. I know there's a lot of people too, but this is a really good thing. So next week, please remember, like someone needs to take charge of the other. I won't forget. Maybe Haiwan, I can appoint you the leader. Can you set up a meeting agenda?
I think Haiwan is the most appropriate.
Yeah.
My vote is for you, Haiwan. Mostly because I don't want to do it, but also because I think that you're better than me.
Either Haiwan.
I listen to you. I listen to you, man. I listen to you. I do whatever you say.
He's never said that to me after working for 4 years, you know. He only says that to you. He will never say that to me. I listen to whatever you say, Kedar. No, but maybe Haiwan, the thing is, many of this is solid states. I think Haiwan, maybe you can do it, and Cheng Wang should take over at some point. But
yep,
I don't know what Cheng Wang's progression is.
You know, you mean the Notion thing, right?
Yeah, set up the Notion. And then put up the link on the WhatsApp chat.
I'll be straight. I want to do this because I see every time Shuya he was using Notion on his matter descriptors, invariant and equivariant thing. I'm so envious. So I will take care of it and ensure it's implemented before the next meeting.
And work with Cheng Wang on this because I think it's a nice way to track the projects. And it's a one-shot view, and I think I usually don't say manage anything. Slack would have been a good way to do it. I know, but I just feel like Notion is really good because we worked on the Wyckoff transformer, and you can assign different people to different tasks. It's really fantastic at task management. So
I gotta say that Notion is phenomenal. That's how we run the A lab. And frankly speaking, without it, it would have taken me 2 months to catch up to what's happening and how.
There you go. I think
it's the best thing ever. Please let's use Notion.
Absolutely. So let's do it. I want please work with Cheng Wang because the DJS stuff that Cheng Wang Delvin should be more familiar with what are all people working on. And then, you start to include people who don't even attend the meeting. Like you think, I don't know, she should start attending the meetings at some point. So this way, like all the people working have their own tasks and what you're contributing to it also builds up to the papers and everything very clearly. Okay, so we should do that. Okay, go ahead. Keep it short, 10 minutes if you can, please.
Sir, okay, so this is actually work that me and Pepe have been doing in collaboration with Torben from University of Munich.
Danny?
Sorry?
Who said Danny and Pepe?
No, sorry, no, me and Pepe. We are working with, we are working with this guy called Thor. So Cheng Wang is also involved in the discussions. So I'll just very quickly run through what the model is, what we are trying to do. So this was the original paper that was published in NeurIPS the year before. So the idea is that, right, if you want to do compositional training, straightforward, right, you can just use some vectorization of your encoders. So the smart idea they had was that, okay, if you were to brute force this for like multimodal data sets, that means you do it for bandgap, you do it for MEM loss, you do it for some elasticity data, blah, 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 blah. All the MapBench data sets, right? You actually get a better join loss. So this is what the field moving in. So Shuya has a counter idea when I was talking to him recently, but I won't talk about that. So essentially, so this is the goal. So we got in touch through what's the Singaporean guy? Elton Pan's name. So we got through in touch with Elton, and then he recommended trying this out. So how to adapt it to our ZT dataset? So this was the ZT dataset that we had from Korea at first. So the idea is that, right, we can use empty encoder. So let me take the laser pointer here. Right, so if we just encode the compositional space with some random masking, so this is just to improve the generalizability. They determined that 512 latent space.
Sorry, what is CPD?
Sorry, I cannot remember what CPD stands for, but it is the latent space.
Why is the latent space an input to the encoder?
No. So you take pure composition, and you encode it into some latent space.
And why is there a CPD at the bottom left?
Is something composition, something masking. That's what it stands for. That means, right, if you have like 4 elements in your composition, for that specific data point, it would randomly mask one of the 4 elements. So they did some empirical testing. They found that it's actually good to do like masking one element for every 3 to 4 elements across the whole data set at a randomly. So they found that this actually improves the overall loss. So there's no theoretical guarantees. It's just empirically they found that this works. So remember, the empty encoder itself is trained on the multimodal data sets, which is I think 16 different data sets. So essentially, this latent space that you're looking at right here is a latent space that works well across different properties.
Okay.
So now to use this latent space for our purposes, we concatenate temperature 100 times. So we have to do it 100. because right is 512. So if you only have temperature once, the information gets lost. So we did some testing. He did 10, 100, 200, and so on and so forth. 100 seems okay. Concatenate everything and then retrain. Then now do a further training step in some standard deep learning NLP, and then we can get our typical like properties, right? Like conductivity, CVEX, and ZT and whatnot. So the issue now was that when we first look at the data, so we still outperform CrabNet. So CrabNet is the previous style of how the model works. MT encoder is the higher version. Composition is just a normal one-hot encoding on a gradient boost model. So obviously this is going to be the worst. But you notice that it's still not very good. Even on MT encoder, we're still getting this kind of funny strips. So what we did was, right, we actually went to observe what all of those little strips are, right, for all of the so-called problem compounds. And we noticed that they tend to show up because of these. So Pepe and Cheng Guang actually read through and then they found that, okay, some of these compounds in the Korean data set shouldn't really be there because of these reasons. I went to double check the DOIs. There were a lot of like wrong synthesis methods. So this is basically the same problem that we had with the ChatGPT paper back then. So you still have to do some manual testing. And surprisingly, after we just trim away those, right, you will see how drastic the improvement is. It's drastic, just by removing the problem compounds, you get a decent working model. So with this, we can actually do some validation.
Well, I understand one thing. The problem seems to be a problem with like mislabeling certain things, not with the actual data, right? Like no matter if you're unsure the polymorph, if you look at your embeddings, it's all elemental embeddings with some structure. It shouldn't matter, right? The data is still correct.
Data should still be correct.
Because eventually some composition, maybe I don't know what's in the structural embedding, plus some structure and the ZT values. I don't think that's wrong. So even though these labels are wrong, why would you remove the data?
So my guess, my gut feeling, I cannot say this 100%, is that because now we are, remember, the encoding itself is really fixed. We don't actually touch the encoder. The encoder is pre-trained on the multimodal data sets. What we are doing now is training this MLP. So while the MLP, if we are still using the correct latent space, the MLP is not able to capture these properties from that latent space for these compounds. So the idea is that there is some further deeper like interactions, like it could be a structural interaction or some of these other like mechanisms.
I would recommend looking at the input to that MT encoder to see what all information is in there. Are there charge values? Are there structure values and so on? Because that you need to prove why this sort of mislabeling can cause a problem with the encoder encoding the information in latent space.
Okay, I'll do that. I'll work with Tom on this. So, okay, the model basically looks okay now. The idea was that it's computationally cheap for him on his cluster. So in Munich side, he just basically ran it 10 times with random starts, right? So we can get an ensemble, so we can get variations. This is like what Ifan already did last time for the neural network ensemble. So we have 4 base data points. So these are the 4 compounds that Pepe says is very high fidelity in terms of the experimental like data that we have. So just looking at the ZTs, right? Not perfect, but the shape agrees upon. It's still within the standard deviation for most of them.
Are you predicting one point at a time?
We can predict temperature by temperature by temperature.
So is there information leakage? This is one of the biggest problem we have with them.
If you're talking about so we already accounted for that. So when we did the train test split, we split it by family of compounds.
So every temperature for a particular family is only in the test bed and only in the bed. Not in
exactly.
Nothing in the training bed. Okay.
Yep. So that's already accounted for.
You're not actually predicting the whole curve, the ZT. You're plotting point by point still, and then replotting it like this. Is that right?
So when it comes to the inference, right? What Paul did was he just took every 10 degrees, 10 degrees, 10 degrees. I mean, it's arbitrary, right? You don't have to do such a small time step, like temperature step. I mean, you just need enough data points to form a curve. So we kept ourselves to 300 to 800 Kelvin because that seems to be roughly like the interesting range. So the data set itself includes data points from all the way down to 0 Kelvin, which we already removed, and data all the way up to like 1200, which we also removed. So we kept at 800 as a rough stage, right? Because sometimes it's hard to also include melting points.
Okay.
So the idea now is that we can actually do the optimization. So we had a very baseline screening. So Chengguang and Pepe had a talk, and then they decided that these are like dopants of interest that we highlighted. So what we did was I came up with a permutation script that would iterate through up to 3 different dopants onto germanium telluride.
So the base material is the same.
It's still germanium telluride.
Oh, so all of this is only germanium telluride data?
Only germanium telluride candidates.
Okay.
Then we would have up to anywhere from 1 dopant to 3 dopants, and in step sizes of 0.1. So that means I can have up to, I'll show you later some of the candidates. So the idea is that we first started by looking at the aggregate ZT, area under the curve of the ZT. So we wanted to optimize for compounds with the highest area under the curve. So these are just some of the top 20 compounds that flagged out and the predictions for their properties and pure ZT. So this is, at this stage, this is what we have. This is my last proper slide.
But there's nothing beating state of the art here.
Yeah, unfortunately.
But can you do an exploration with the BO? This is not BO, this is just forward model, right?
All right, this is essentially a one-shot optimization. So then this is where we are at the impasse, right? So my thinking process is that you can't really do significant optimization for large data sets in deep learning, because adding 1 point by 1 point does not meaningfully change the predictions of such big data sets to begin with. So
the lattice space fully with this discretization?
Sorry?
Are you sure you have explored the latent space fully? Like, are there regions that are unexplored? Or
there definitely will be compounds unexplored. So we did not visualize the latent space for these compounds. But because remember, we are just looking at germanium telluride as a start first, because we wanted to be more discrete. So there's nothing stopping us from going to pure latent space, but the latent space itself is huge. It is 512 plus 100 temperature concatenated. So it may not be reasonable to do BO on this.
but you just you further reduce some PCA, right, or something, and then you do optimize the PCA and do an inverse transform back to latent, something like this.
Possible, something that we will try out. So I have the checkpoints. I'll just ask Thor how to figure out how to process the latent space.
I think that's something I shared yesterday with you, right, Andre? The latent.
Correct.
Look it up and see if you can use some of the strategy and just push for high.
Yes. Remember, because these are compositions, right? So compositions, you can't really get, you don't have a perfect continuous space no matter what you do. Yes, it's always discrete.
Sure.
Yeah, especially if you have that constraints, right? Like in our case, we wanted to limit this to the germanium has to be at least like 50%. And then we didn't do anything to the telluride. So it's not, it's a lot of engineering tricks there that we have to figure out. Yeah.
I mean,
so the end goal is, right, when do we want to actually get started on making compounds? Do we want to figure out candidates with like state of the art, or do we just want to explore within this family, or what?
I think if you have to beat state of the art with prediction, try it. Otherwise, I don't see anything crazy here.
What's the definition of state of the art? Is state of the art highest peak ZT or highest aggregate ZT? Either. Okay.
Yeah. Actually, I don't care.
Are we limited to any compounds or whatever that Chengguang can make?
I would stick to germanium telluride because we already have a lot of data and experience with it. This is a proving of this approach should be, if for germanium telluride, if you're able to show that you're getting to the state of the art with the prediction model and you can beat the state of the art with some slight extension of it, we can easily try it because there's people trying it already.
Pepe, could you chime in here for these 4 high fidelity compounds you gave me? How close are these to state of the art? Because I'm not familiar with the literature.
Far.
Can you give me the data points?
Yeah, I can give you the data points.
I think the max is like 2.7 or something.
Yeah.
For the germanium telluride family.
So Kanish took the paper in advanced material with germanium telluride based compound. I forgot what they put in. And they went to review in both Science and Nature, got rejected. And they ended up.
Yeah, that is 2.5 something. Recent paper in February.
Yep, exactly.
Yeah, I think I was reading that paper. Let me show. It is Kanish.
Add it to the WhatsApp. You can add it to the WhatsApp group. Yes, I mean, the point would be these methods, and I think it's the same line of we have to beat state of the art, because otherwise it's just another paper in different models, nothing new, that kind of thing, you know. So that's really where we want to go, is to beat state of the art. You could look at other explode compounds if we don't want to germanium telluride. So you can look at one of the newer, like some family of compounds that have recently been, you know, then you have a higher chance of success. Okay, but I don't know what they are. Okay. So
At the end of the day, this is capped by what Cheng Guang is comfortable making also, right?
Right, but I mean, in general, we are able to make metallic alloys and stuff. So you could look at some, I don't know, some family of compounds that is relatively new to thermoelectrics, but people haven't done a lot of optimization already.
Okay, so that's like so-called low-hanging fruit, right? Because it's still lots of unoptimized space to squeeze. Yeah. Okay. Ken, I'll continue working on this. So I'll just look at the latent space. I'll see if there's anything we can do to play with the latent space.
Right. I think that then it'll increase in terms of both novelty of method and novelty of results. I think that'll be it.
Okay. And then I will also consider maybe more families. Ken, okay.
Okay.
Yeah, okay, this is not important. Okay, that's all.
All right.
Okay.
Any last comments from anybody? No. We have 2 to 3 minutes. Go ahead. And then next week we start off with Delvin and the catalysis project, perhaps, right? Unless I'm missing something. Also, Pawan, it might be good to share your work on the thin film stuff that you've done already.
Yeah, sure, definitely.
Hyman, see, you're in charge of this, man. Set the meeting agenda, who starts. And so I think we'll get that going. Okay. Very exciting stuff. There's a lot of things happening. Are you sharing Jayanta or no?
You kicked out?
No, he's there. He's just sharing.
Oh, it's there.
Yeah, I've seen this. I see. Oh, yeah. Underdog, yeah. Okay. Yeah, I mean, it's a tricky thing. So, I mean, I think I had a brief chat with Pepe on WhatsApp. I had not this data. In general, the key here is, I think, your power factor numbers are already pretty good, right? So if further doping is not going to change your power factor by much. So my thinking here is that even if you introduce more dopants, your overall thermal conductivity still doesn't go down significantly. I mean, actually, your 10% antimony is quite good in terms of thermal conductivity, right? 1 watt would be crazy. But I think the amorphous limit is like 0.2, right? If I'm not remember correctly. Yeah. Yeah, so you can push it. So either we do more elemental doping, or the paper I saw recently, which I read somewhere, was like the silver copper telluride, which I think high temperature forms the same crystal structure as cubic germanium telluride. So you literally have alloying of silver copper telluride with germanium telluride. But I don't know if we can do that with DJS and stuff. So and then do SPS. So it needs a little more thinking. I think Pepe, you can decide what is the best avenue here. Figure out Jayanta. Spend some time thinking about it and see what makes sense, right? I mean, the numbers are great. It's just that thermal conductivity is relatively low. But what is the problem here? Is it underdoped? Yeah, 300. Is it because of mobility decrease? You see back. I mean, okay, for example, if you get 160 CVAC, You don't,
is too low.
but if you're controlling that doping, if you get like 160, 180 Cbac, and then you get your conductivity with 1000 Siemens per centimeter, how much does that move up your power factor? Does it increase it substantially or not?
Yes, it should be. It should go up to 1 milliwatt range, 2 milliwatt range.
Yeah.
And now it's hundreds of 0.1 milliwatt range.
It's not even 0.1.
The blue curve is close to 0.1.
No, it's 40 microwatt per centimeter square. It's already very high.
It is 0.4 milliwatt, yeah. At high temperature, yeah, 0.4.
Not 0.4, right? 40 microwatt is 0.04 mic, but this is centimeter.
Yeah, so if you convert this 0.4 milliwatt.
0.4 milliwatt, yeah, okay, I see.
Yeah, milliwatt per meter Kelvin square.
Yeah, so that's correct. So if just do the simple number, right? If you have a 160 and you have a conductivity of 1000, does that get you to a power factor of I don't know what, like
supposed to be 1 milliwatt.
Possible, right? Yeah, actually, if you look at this, I'm just doing simple ballpark.
It's 4 or 0.4.
So let's say you're able to get this trend, right?
It's microwatt per centimeter height.
Yeah.
And it's like this. If you get this, then let's say the Cbac stays about the same, you should be able to push this up to about 3 times higher. 2 to 3 times higher. So maybe it's a doping question and not a thermal conductivity question. Please think about this a little bit, and then we can decide what to do.
This is not 0.4. This is 4 milliwatt per meter Kelvin square.
Oh, it's microwatt, 10 to the power minus 3 and divided by 100. So it's
10 to the minus 1. 10 to the minus 1 is 4. This is 4.
4 million. That's why I thought it's pretty high.
Because micro is minus 3, centimeter is minus 2.
Wait, we can do the math later. I gotta.
Yeah, sorry.
You guys can stay if you want to chat, but I think the key will be please think whether it's a doping problem or a thermal conductivity problem. Okay, that's the question for you. Very simple. Okay, think through. Do you think you're going to win by doping it properly? Because you now have the 5% cadmium and then 10% antimony. What you've really done is de-doped it quite a lot, right? So if you think about your standard picture, very easy. All of us know this, right? You've gone from here perhaps to here somewhere. I don't know, right? This is in terms of doping, right? Deep doping and power factor. You guys know all this. Pepe knows all this. S square sigma. So the question is it a doping problem or is it a thermal conductivity problem? Can you please think about it a little bit before you decide what to do next? Okay. All right, guys. Thank you. Good to see all of you. See you in a bit, in an hour.